This is the next video in the chapter on electronic structure and periodic properties. We were just discussing atomic radius. We had just rationalized why the radius increases as we move down a group, as you can see in this photo. The circles get larger as we move down a group, but we also predicted that the size would get larger as we move left to right, and we were faced with the fact that that was not true. So now we're going to try and justify why that could possibly be true. Okay, so we said we predicted that as we moved left to right and we added more electrons, that the radius would get larger, but this is not experimentally determined to be true. So we're going to need a new feature besides just the number of electrons to help us explain this. So we need to understand a feature called the effective nuclear charge. Represented by Z sub EFF. We need some more space to draw pictures, so we'll put it over here. Okay, so you may not know what effective nuclear charge is, but you should be able to figure out what nuclear charge is. We've already talked about it before, we just haven't used this name for it. When we talked about it before, we called it the atomic number. So nuclear charge, atomic number, same thing. We called that Z. So the nuclear charge or the atomic number is the number of protons in the nucleus. Or you can think about it as the amount of positive charge in the nucleus. Because the electrons are negatively charged and protons are positively charged, and these attract each other. So we need to understand how strong of a pull that positively charged part has. So the effective nuclear charge, you write that as Z EFF. And that, the effective charge, is the positive charge felt by a specific electron. And so this number is always going to be less than or equal to the entire positive charge. So we have the entire positive charge, and then the effective nuclear charge is slightly smaller than that. So how could that happen? Why would the positive charge decrease? Or what, rather, the positive charge felt by an electron, why would that decrease? So let's talk about what it feels like to be an electron at the outskirts of an atom. So when an electron is super duper far away from the nucleus, it doesn't always feel the full positive charge of the nucleus. And this is because there are other things, negatively charged electrons, in the way that block that positive pull. Other negative electrons are in the way. And we're going to use an analogy to understand this. We're going to pretend that we are in a forest with our friend, and we are trying, our friend is ahead of us on the trail, and we are trying to find our friend. This is supposed to be a person with binoculars or a person shielding their eye. So let's say our friend is a little bit ahead of us, so there's like a couple of trees in the way between us and them. But we can still see our friend. The branches aren't too thick. We can move our head to the side a little bit. We can still see our friend. But what if our friend got way ahead of us on this hike? Had their earphones in, totally weren't paying attention. They're way over here now. And there are like a whole bunch of trees in between us and them. These are supposed to be trees. So if there are lots and lots of trees, that person is way, way far away from us, we're going to have a difficult time seeing them. We're not going to be able to see very much farther than this first tree, and we're not going to be able to see our friend. So this is similar to how the electrons search for the nucleus. So the friend that we're looking for, that represents the nucleus. That's the positive charge that electrons feel the pull from. Feel the pull to catch up with your friend. And these trees, they represent core electrons, the ones that are the closest to the nucleus. And in this second atom, there are a lot of core electrons in this picture. And then you and your binoculars, you are an electron on the outside. You are one of the valence electrons. So you're way out in the outskirts, trying to see into the center, but your view is being blocked by a bunch of other junk that's in the way. And so the way this works is that the farther away the valence electron is from the nucleus, the harder it is for the electron to feel that positive pull, because the positive pull is deflected by all those other negative things that are in the way. So core electrons, the trees, shield the valence electrons. That's you. From the pull of the nucleus, which is your friend. So this word shield, this is going to be a word that gets used a lot in talking about size and periodic trends. The shielding, that's what these core electrons are doing. They're shielding the valence electrons from that pull. So now that we know about shielding, let's revisit what happens to the atomic radius as we move across a period. So as we move across a period, what happens? Every step we take involves adding a proton and an electron. And let's think about the effects of both of those additions. So specifically, how does it affect the Z effective? So as we add a proton, we're increasing the number of positive charges. So we're increasing the total positive charge of the nucleus. So we have a stronger Z effective because there's more positive charge. And if there's more positive charge, it's pulling harder on the electrons, and that decreases the radius. It pulls them in closer, the more protons you have. We also add one electron, but remember, when you add an electron, you add it to the same subshell. So we're basically adding a tree to our left or right while we're trying to find our friend who is ahead of us. So the valence electrons don't shield each other very much. So this doesn't have much of an effect. Adding a large number of electrons, like when we step down a group, does have an effect, but only adding one electron doesn't do very much. So valence electrons don't shield each other very much because they're in the same space. So if we're adding a proton, which is increasing that Z effective, and we're adding electron, which isn't doing very much, then that allows us to explain the trend in atomic radius decreases across a period. And you can, of course, memorize these trends about which way the radius increases in the table and which way it decreases. But better than memorizing is understanding how the trend works. So thinking about how those core electrons decrease the effective pull of the positive charge and make this a more dramatic effect. So here in our picture, as we move from left to right, it's not a very significant change, but you can especially tell over here in these first couple, the left side is where the larger sized radius is. So here, this is data that shows the measured atomic radius for each of the different elements. And you can see one particular period starting at the highest point with lithium and decreasing down to neon. That's for the second period. Then the third period here from sodium down to argon. The fourth period, potassium with a little bump in the middle for the D block down to krypton. So we are decreasing as we move from left to right, and as we move from top to bottom, lithium to sodium, potassium, we are increasing down the group. And then that was the first periodic trend, atomic radius. In the next video, we'll talk about the second periodic trend, which is ionization energy.